All right, folks, welcome to another PyMCon event. Today we have Dan, who's going to be talking to us about multi-output Gaussian processes. So PyMCon is a rolling web series. This is the second event we've had. The first one was Dante Gates talking about data generating processes. And unlike other conferences where it's sort of a one and done event, we have like I mentioned, it's a rolling web series with multiple sub-events per event. So Dan has given an interview. You can find that on Discourse. That was the first part of this event. He published his code and his blog, his code repository. It's probably the second part, and this happens to be the third part. So all the details are on pymccon.com, which we will post in the chat. If you're interested in Dan's talk or in any of the other talks, there's a wealth of information you'll find on our Discourse and on the website. And if you are interested in giving a talk, if you would like to come in, and I keep using the word talk, but if you're interested in running an event, either as a volunteer or as a speaker, the CFP is always running. So you can go online, go to the CFP header at the top and submit your proposal. There's a nice Google form that'll tell you how to do so. So with that, the last 2 points of logistics, we are going to be prioritizing questions from the Discourse. So go there to post your question, but we will also answer questions posted in the chat as well with a second priority. So I will hand it over to Dan. I want to thank you all for being here, and we'll get started with the meat and potatoes of the presentation.
Yes. Hi, everyone. Thank you for coming to this workshop. And before start the workshop, I would like to thank the PyMC team and also the support of other people for that event to be happened. And now let's start. Let me share my screen. So the content of this workshop today will be in this GitHub repo, which I will put in our chat as well. So in today's workshop, I divide into three sections. Here, and the talk is on multi-output Gaussian processes. But we will start with some simple about linear regression, and then we introduce some review concept about Gaussian process. And from that, we will move to some more concept in multi-output Gaussian processes, including the reason why we need to use multi-output Gaussian process and a couple of models like Intrinsic Coregionalization model, ICM, or linear Coregionalization model, LCM. And then we will have some example how to implement it in PyMC at the end, right? And the focus of this talk is more on introductory and focus on less math, but more on the code, right? And for the first talk here, if you click on this one, it will go to the slide I will use for that. And if you click on the open Google Colab here, you can run the code on the Colab. But one note here is if you want to run the PyMC version, we please copy this live code here and put it in the beginning of the cell. So this one I have just do it a couple of minutes ago. I copy the code at the top here and then run it. And you might need to restart the runtime as well. So after install all this stuff here, it will show you the button called restart the runtime. And if you click that, and then after that, you can command it and click run all here. And that will run all the notebook or the code inside here. And at the end, you can see that the listed PyMC version here is version 5. All right. So this notebook I converted into a slide. So I will using that slide for this. So let's go start to the first section on intros to PyMC GP. And another note here, the second part is just a slide, the third part is a notebook, and it run a little bit slow on Google Colab. So if you run the third notebook here, I would recommend you to run it on local environment using some guideline here. And maybe at the end, I can show you some trick how to make that process faster, right? All right, let's start with the first part on introduce to Gaussian process. So we have a training data set D, which and observation x, y, I, y, right? X, I, y, I from 1 to n. And here, yi is scalar output and xi is a input vector. And we can stack it together to have x as a matrix and y as a column vector here. And a general model will be yi equal to a function of fxi and some parameter theta plus some noise epsilon I. And epsilon I here will be assumption as a normal distribution with mean 0 and sigma standard deviation. And later for simplicity, we assume xi is scalar, but it will work for xi as a vector as well. So in a simple model, we can use a linear regression. And in linear regression, we assume the fxi here will be equal to beta 0 plus beta 1 xi, right? And so the theta here is a vector of beta 0 and beta 1, 2 elements. And if we replace it to our function before, so yi here will be equal to beta 0 plus beta 1 xi plus epsilon I. And we learned through Bayes' rule that how to calculate the posteriors based on the posterior of theta here given x and y will be equal to the probability of y given x and theta multiplied with the posterior of theta divided to the probability of y given x. So it's this term is called the prior, which is our assumption about the parameter theta before we see the data. And this term is called the likelihood and or our data. And this term is called posterior is what we changing about our assumption, our prior assumption after we seen the data, right? And the term at the below here is we need to calculate using some integration. And they call it evident or marginal likelihood. And this sounds complicated, but actually in bucket like PyMC, what we actually need to do is we just need to specify the prior for theta and then specify the likelihood. And after that, the bucket like PyMC can calculate our do sampling and calculate the posterior first. So the sampling actually they also have to approximate the integration here. So we actually don't need to care a lot about that if we are focused on working with data and try to understand and apply that data. So they have different kind of sampling like give on NAS, and this can help us to get rid of the worry about the integration and other stuff. And after we have our posterior distribution, right? And then if we have unseen data, we can calculate the predictive posterior using this one. And again, this integration here about the theta here is also have already have a function calculated for it. So I will show some example to show you how to do that in a later part. And from this one, you can see that in the linear regression, or is it some kind of parametric model, because what we want here is we want to estimate the f function by using theta. So what we do is we estimate the theta through beta 0 and beta 1 here, and then from that we can estimate the f, right? And we can have a more complex function with more parameter, maybe beta 0 plus beta 1 xi plus beta 2 I square, if we have a quadratic function, or we can go more and more like x3 something, but it will be like overfit or somewhere very complex. So in case we only want to focus on the forecasting, and so we don't care much about the parameter beta. What we want to do, maybe we can estimate the f function directly. So thus it get to the direction of Gaussian process. So the Gaussian process is what we want. We want to estimate the f function here directly without all the parameter beta 0, beta 1 here, and the f here is called a latent factor. So for this Gaussian process, the function f here, what we need to do is we need to assign a probability distribution over f, and according to the Rasmussen and Williams in the book on Gaussian process, they define Gaussian process is a collection of random variables and a finite number of which have a joint Gaussian distribution. So basically we start the f function evaluate in different x value here at a column vector, and we assume that the latent value here of f will be distributed as a multivariate normal distribution with a mean vector m and with a covariant function kernel. Covariant function, or they call it kernel, and we can represent this one at the shorted notation here called ZP with mx and kxx prime. And normally the mean function here, we can set it as 0 or linear mean, and what we more interested in is in the covariance here. So there is different kind of mean and covariant function in Gaussian process. Here is just the several popular one, and the first popular one is called radio basic function, or RBF, or so they have a math equation like that, and they can also call it at exponential quadratic, because we have a exponential function here, and also quadratic of x minus x prime square here. We have a square, is that what they call it. So in PyMC we can use this kind of function to represent that kernel, right? And this one is some example. If we change the parameter of they have the lambda here called length scale, and sigma here as eta here. So this one will change the scale of the y, and the lambda here will change the length scale of between different x. So if lambda is small, it will be more near each other, and the change will be less. And if lambda here larger, you can it is more smooth, and different x will be have different distance, larger distance as well. So there are also others covariant function here like rational quadratic, and it's actually a generalization of the exponential quadratic here with the alpha here. I'm not sure if I call it the alpha here the right name, but it is some kind of generalization with for the previous one. And we can also have others covariant function like periodic, which they have some like the up and down, like sin and code in our mathematics, and also we might have a linears here. So there is a lot of others covariant functions, and here I put some references that later you can have a look at PyMC documentation. But basically, in Gaussian process, we will use different covariant function to represent and learn the data in that to represent our covariant matrix. We will go to some example. So this is some data set that Chris have his talk in some PyData a couple of years ago, and he data set about salmon data, and we have here is the x-axis is spawners, and the y-axis here is the recruit. So our data is something like that. And first we can do a simple linear regression, right? Like we discussed before, if we assume that fxi theta equal to beta 0 plus beta 1 xi, right? And we have some assumption about our parameter like beta 0 and beta 1 here will be a normal distribution with a standard deviation here 50, and the sigma here also a half normal because sigma here is the standard deviation it need to be positive. You can also use others other distribution as well, like right. But here just make it simple. We use this one, and as mentioned, we just in PyMC model, what we need is we just need to specify the prior. Here we have beta 1, 0, and beta 1 and sigma, and then we define the likelihood. The likelihood actually is our mean function, which is equal to this equation, which is our this equation, right? And then we have a sigma for the error term here in here, and then we specify our observation. So that is all we need to do. And after that, I think let's have a look at the prior before we see the data. So here is the normal distribution for beta 0 and beta 1, and here is a half normal for sigma, and we can do the sampling to get our posterior distribution. Right? So in PyMC, we just need to call the pm.sample, and the default of sampling method here is NUST, no U-turn sampling, and we will have our posterior. And you can see that now our posterior is a distribution of beta 0 and beta 1 chain, right? And also our sigma here before it is half normal, but now it's like a little bit more normal, but it is just one. So we can also do prediction as well, right? And for that we can plot different sample different value of parameter, and then we calculate the line to show that here is the prediction of our linear model, regression model. So that is how we can do it in linear regression. What about Gaussian process? In Gaussian process, we assume that the f is here instead of a parametric plot theta here as beta 1, 0, beta 1, right? We can represent it as a Gaussian process with a mean function and a covariant function or a kernel. And in our case, for example, in this example, for this data set, we will use a linear mean function and a exponential quadratic kernel that we just saw previously. And the output also the same. We need to specify our prior at this time is the prior for the kernel. For the kernel, because our kernel here, if you remember that we have let me bite this one. For example, this kernel, we have covariant exponential quad here actually equal to only this part. Exponential of this function. We have also some what I call it sigma square here or eta square here. This one is not in the PyMC, so we need to create another variable here and multiply with one here. So one note here is a exponential quadratic in PyMC, is only the exponential part, all right? So if I come back to this one, so this one is our exponential part, and this one is our eta square on the top, right? And so this is our kernel, and this kernel it depends on some we mentioned a length scale that we can have some the prior here, and also from the scale of y we have some prior about that here, and we can also have some definition about the mean as well. From that we can set our likelihood similar to what we have. So we have the specify our priors and we specify our likelihood, right? And after that, we do the same thing. We can do this, the PyMC can do this sampling for us. And then after that, we can see the posterior here, but for some parameter in our kernel, right? And from that, we can also sampling to calculate the predictive posterior. So before, if we use parameter theta, we need to, and if we have a new unseen data x star, and we want to calculate y star given x star and our data we seen before xy, we can do integration to the theta here. While if in case of Gaussian process, we will do integration with the latent air function. Just that difference. And in PyMC, we just need to do conditional here and do sample posterior predictive of that. And after that, we can here we get three sample of that in our chain of our predictive posterior of y, and you can see here is how it fit with our observation. And if we there is a plot GP distribution in PyMC.gp.out, and we can use that to put the posterior predictive in that, and you can see that here is our fitting model for that data set. So I have some references here for that part, and the data set and most of the code is from Chris talk in 2019, and also other references here for the mean function and the notebook also here. I'm not sure if I should stop here for a couple of minutes if anyone have a quick question on that part. If not, we will move to next part. So we start from Gaussian processes and we move to multi-output Gaussian processes. Yeah.
Dan, we have one question. I don't know what this is in reference to, but there was a question of if you can use flat priors.
Of course. So I think they mentioned about linear regression here, right? A second.
Yes, in linear regression.
Yeah, and things. Nice. Oh, I think it should be here, but here, this one, right? Yes, of course, it is the priors, and the prior is our assumption. And if you want to have a flat distribution here, it need to be start from 0 or above, right? To the other side, the positive side. There is some, I think there is some paper talk about how we set prior, and it also depend on our domain knowledge as well. So there's is informative prior and informative prior as well. So I think in theory you can, right? We can define a prior, but the prior should have some knowledge in that, or if we don't have any knowledge in the prior, we can set it flat or normal with a very large standard deviation. Yep. Hopefully that will answer the question.
I think so. Feel free to move on.
Yes. So that is the first part of our talk, and in this part we talk a bit about basic concept of Gaussian processes, right? And now we will move to multi-output Gaussian processes. So this one we consider as a single output because we only have one data set. But now we move to maybe 2 or more data set that have maybe same uncertainty. So let me move to this PowerPoint slide because this is one quite a lot of equation. I will try to go through the equation quickly and show more code, but we also need to have some equation to explain Gaussian processes and its multi-output. So we start with this one with a why. So why we need multi-output Gaussian processes, and the reasons is because in reality there are many cases where several output are affected by the similar uncertainty. So to give you some example, for example, we have the temperature or wind speed in nearby locations, that kind of data set, and all the stock prices in technology companies. So they might have some underlying uncertainty related together, or maybe the currency exchange respect to US dollar, or maybe the EEG recording from our human brain, different location of our human brain, or also other kind of factor or information like crime rate or the rate of cancer in different location, or the soil polluted network. So in general, this kind of data set have a temporal or spatial feature. So basically, the temporal is time series data, and spatial is they have the location, longitude and latitude information on that. So here is one example. Here is the sensor network from south coast of England, and here we have 4 sensors at nearby location, and which will record the the wind speed or the temperature, right? And you can see that here is one part of this one is missing. So maybe because that 4 sensor in nearby location, so maybe they will underlie in with the same uncertainty, and we want to learn from that the other 3 data here to impute the missing value here. Or maybe assume that this one is 4 part in our brain, right? 4 part in our brain, and if we predict the future of the signal, might be some part of our brain we're more certain about that, and we use that kind of information to predict the uncertain part of other part of the brain, or maybe the stock as well, right? So that is the reason why multi-output Gaussian process is useful for this kind of problem. So let's talk about a single output Gaussian process that first. So as in our previous section, we have our data set D, which an element from Xi to Yi or Yi here. And our data set is the red dot here, as you can see. And our Yi will equal to Fxi plus the arrow term here, right? And here we assume this, the Fx here will be modeled by a Gaussian process, which here a mean of 0 and a kernel K. So if we stack the Y together to a column vector, right? It will be as represented as multivariate normal distribution with the mean vector of 0 here, and with a kernel K as a growth. It's called growth covariant function. Sorry, it's a covariant function or kernel K, and plus some arrow term here. So that is one data set. So we have one Gaussian processes. If we have, for example, here we have 2 data set, D1 with N1 elements and D2 with N2 elements. So we have 2 data set here, as you will see. And we assume that this F1 of in the data 1 will be modeled as a Gaussian process of kernel K1, and F2 here it will be modeled as a Gaussian process of kernel K2. And if we want to model that 2 data together, right, we can actually stack it to a bigger column vector called Y1, Y2 here. And if that 2 data set is independent, if it's not related to each other, we can form it like as a multivariate normal distribution with a bigger mean column here, column vector here, and with a bigger covariant matrix, this one, and plus some noise here. And you can see here is a diagonal here is 0 because this is independent. So in case of independent, we can model that 2 output here as this one, right? But what if they are related together? So what we want is we want to have some term in the 0 and 0 here, right? To model if they have some same uncertainty, we want to model that, and that is the aim of the sum of the model proposed in multi-output Gaussian process. That is, we want to build some kind of function to model the cross covariance between this one and this one. So this one and this one is similar, right? So it's we can call it the cross covariance between F1H and F2H, so between this one and this one. And the first model I'm going to introduce is called Intrinsic Coregionalization model, or ICM. And the assumption is that we have both latent factor F1 and F2 here is generated from the same kernel or same Gaussian process. So for the ICM model, the assumption here is K1 will be equal to K2. So let's go through that one for ICM. And in this example, that assume that we have two output and one latent sample. So assume that we have a Gaussian process EY equal to the Gaussian process with kernel K, and from that Gaussian process we sample one sample U1X, and from U1X we do a linear transformation by multiply U1X with some scalar value here A11 and A12 to calculate the F1X and F2X. So to give you an example from that, if we have a EOX and we sample E1X from EOX, Gaussian process from EOX, we have some data like this, and we can transform the U1X here to F1X by a linear transformation. So you can see that the pattern here is similar, but the scale here is different because we have maybe here is the scale 0 to 1, and the scale here is 0 to 5. So the A11 here is 5, right? So it's change the scale of the data, but the pattern is still the same. Same here for F2, and the scale here is just a little different. So from that, what we do is we can stack F1X and F2X together to have a big column vector. And what we do is we calculate the cross covariant function between Fx and Fx prime, and it will use some expectation equation here, which I will not go into the detail. But if we replace Fx with Ex, right, we replace F1x and F2x with U1x, we will have some equation like this one. And because this one, they have the same Gaussian process from the Kx prime before, so we can form it like the covariance of Fx and Fx prime here equal to A multiplied with A transpose. A here is our this one, the vector we have when we transform the E1 H to F1H and E1 H to F2H, right? And it's either the column vector one, right? So A will be a vector 2 by 1, and A transpose will be a vector of 1 by 2. So this one will be, if we define B as AAT, B will be a vector 2 by 2, right? A matrix, sorry, a matrix 2 by 2. And if we replace B here, we will have covariant Fx prime here will equal to B times Kx prime. And because B is a vector 2 by 2, we can represent it as this one. And in PyMC, we call B here at a Coregion kernel. And this one, we also have different kernel that we just mentioned previously, right? Like exponential quadratic kernel that we mentioned. And here's this one, the B here, we call it a Coregion kernel. We will talk a little bit more about B later. So let's generalize the ICM a little bit more if we have two latent samples. So here we have two output, but we have two latent samples. So so here we also assume that these two latent samples also form the same underlying Gaussian process with kernel K. And from that EOX Gaussian process here, we obtain two samples, U1X and U2X. And we do the same linear transformation, but now we have two samples. So we have two scalar value A11 and A12 or A21 here. to transform that, and we sum it up to calculate F1x. Similarly, we have different scalar to add it up with U1x and U2x here. So general here is an example of U1x and U2x, and we do some linear transformation, combine just two together with different coefficient here. So we can obtain the F1x and F2x, which will have not only the scale different, but the pattern is also different, right? And similarly, we can calculate the covariance or growth covariance between the Fx and Fx prime by replace the F1x, F2x with U1 and U2x, and then we define the beta here will be the sum of two multiplication vector A1 and A2 here. And again, this one is A1 here is a column vector, and with the same thing, this one will be 2 by 2 and not 2 by 2, right? And the shape of the B here still 2 by 2. So that's why we can also represent it as the matrix here with 4 elements of B here. So in the end, with ICM, if we have two data sets and we stuck out latent vector together to form a bigger column vector here, it will be a normal distributed multivariate normal distribution of a mean vector here, and with this new covariant function, right? And this new covariant function is actually, it's called Kronecker product. So let me have a quick review on Kronecker product. So Kronecker product between the matrix A with matrix B will be equal to each element of matrix A multiplied with matrix B, and we stack it together to have a bigger matrix. Right? So for example here, if we have this matrix and we connect a product with this matrix, what we're doing, we get each element here 1, 2, 3, 4 multiply with this matrix. So we have 1 multiply with the matrix, 2 multiply with the matrix, etc. Right? 3, 4 with the matrix, and then we multiply this one with each element here inside that matrix. And then we can have a form a bigger matrix here. So if we have A here with a shape M by N and B here with a shape P by Q, we will have a product with the shape PM by QN. Right? So here 2 by 2 multiply Kronecker product with 2 by 2 will be, we have a 4 by 4 matrix. So if you see this one, right? This notation here, and we come back to our previous this one. So this one actually is the Kronecker product between matrix B with matrix kernel K, right? So that's why we can represent the the covariant function here as a Kronecker product between Coregion kernel, we call it Coregion kernel B, and the kernel K. All right. So that is one kind of model called ICM, and where we assume that the F1 and F2 here is have the same underlying Gaussian processes with kernel K, with one with the same kernel, right? But we can do a generalization of that of ICM if we have Q kernel, Q different kernel, K1, K2, and KQ. So the LCM or linear model of Core's generalization actually is a generalization or the sum of different the ICM together. So that is two most popular model in multi-output Gaussian processes. So the same thing, we calculate the covariant function, covariant function, and at the end we will have something like that. The kernel will be sum of the coregional of Q Kronecker product with the kernel KQ, and we sum it together. So this is for the LCM model. So in PyMC, the B here, we have the covariant or the kernel Coregion, which help us to represent the matrix B here. And underlying that is it implements not a connect product, but a Hadamard product. So why we need that? Because the Hadamard product has some feature that have it later. So I will go quickly on that as well. So the Hadamard product between the two matrices actually is the element-wise product. So we get the matrix A with M and by N multiple Hadamard product with the matrix B, M by N will be equal to matrix C, also the same shape, by we multiply each element of A with each element of B together. So here is an example of Hadamard product. Is the element-wise product. So this element here will equal to A11 multiply with B11 here. And basically we can convert a Kronecker product to a Hadamard product. So if in our previous example, we have example of this one, the Kronecker product between this one to this one. And we show that we equal to each element here multiply with that matrix, and we start it together here to have a bigger matrix. And if you see that this one actually is a Hadamard product of this one, this matrix multiplied with this matrix. And if we see it clearly, it's actually that a broadcast, right? Broadcast of the one here to the same side of this matrix, right? The same type of one here. So the one here we have 1 1 1 1 for number one here, and multiply with this one element wise multiply with this one. So this just some kind of broadcast and indexing, right? To convert this one to this one, and also broadcast this one, small this one to this one. This can help us to convert the connect product to a Hadamard product. And because in implementation, the Hadamard product have some feature like we can swap two matrices together and the results still the same, right? For Hadamard product, but not for Kronecker product. So, and also later if the underlying sampling and calculate the Gaussian process for inference, we need to have some inverse calculation of matrix, and using the Hadamard product will make it a lot easier to calculate. So that is the reason why we need to convert Kronecker product to Hadamard product. So the underlying Coregion here we convert that. I will show you later in an example. So let's go to the example because it's quite theory, right? And what we have here is we have ICM and LCM, and ICM will be from the same kernel, and LCM will be, we can have a different kernel. That's the basic idea. And if we move to the example here, I open this one. So this one is project I work under the mentor of Bill and Chris, and for last year Google Summer Code. And we have some data set here called the fastball spin rate. Fastball spin rate, and it is actually the average spin rate of different player in different game or different date. And from this data set, we get do some normalization for the spin rate, and then we get the top five most popular players. So here we have Roger, which he joined 64 game, Tyler 59 game, and we have, so you can model any output, right? For this one, we will have five output, but you can select 3 or 6 or whatever number in your data. And from that, we can form indexing the game days at our data access, and the data will be something like this. So here is the x-axis, which is the index of the game days, and the y-axis here is the average spin rate of five picture or 5 players we have in baseball. And what we do now is we will try to use ICM or an LCM to model that data set, right? And for ICM or intrinsic Coregionalization model here, our kernel will be the Kronecker product between the matrix B or the Coregion B, right? With another kernel. In this case, we choose a simple exponential quadric, but basically you can choose others other kernel as well, right? And the B here will be equals to W until WT here with some diagonal here. So you can set up the B using that. So here I create we create a guess ICM function. So basically is input the kernel, this one, and the B matrix, this one. And from that we can calculate the Coregion kernel using B, or either if you don't have B, you can input W or Kafka here. And then here we calculate the ICM covariant using the Hadamard product of that two kernel. And because the underlying of that, it is, as you can see, it should be a Kronecker product, but actually in underlying the Coregion here, they already do some broadcasting of the matrix B here. So it converts this one to also the K as well. It do some indexing and broadcasting to a bigger matrix to convert the Kronecker to a Hadamard product, right? And then we will return that covariant. And this ICM covariant, if we stack different output together, this covariant will be the big covariant for all the data, for the output data, right? And it will be the similar thing at our single Gaussian processes. So here, if you can see that we do the same as our previous case for single Gaussian process. We set some prior for our kernel. In this case is exponential quadratic, which they have some length scale here. And also we set some prior for beta using the matrix W here and Kafka here, and then we use the guess ICM. We will define this one to calculate the covariant for ICM, and then we do the same calculate the marginal and marginal likelihood as in our single output Gaussian process. So this is our likelihood. And after that, we will PyMC will do others difficult stuff like do sampling, right? And prediction as well. We just need some specify the conditional, and we can from that we can sample posterior predictive using the trace And here is the plot of our model, and you can see that it fit pretty well with that for. And this part here, you can see that this part is some missing data here, right? I mean, here's some date, some game that that player compare here, not join the game date, but we can like infer that missing data using other data from other player here. And one interesting from this is you can see that the average spin rate from that guy, the Rob Rigger here is significantly reduced here on this point. And I don't know about that, but when I told that to Chris, he mentioned that this because some player, they put some substances in their hand when they threw the balls, and if they put some substances in the hand, it will make the spin rate of the ball faster. But after they cancel that policy, they don't want people to do that. You can see that some players, they performance or the average spin rate is significantly reduced, like this one and this one, while other people here is seem increase and still all right, right? So here is some, and this is for ICM, and for LCM, as we mentioned, we can the LCM actually is the generalization of the ICM. And here, for example, we can use two kernel, exponential, quadratic, and a Martin 32. And we can define a function called get LCM, but the basic idea here is we calculate different ICM and we sum it together, because as we saw before that the LCM actually the sum of k ICM kernel, and after that we can have a covariant function, and this will be the step will be the similar as previously, that we specify the priors and we get our covariant function for LCM, and then we do specify our likelihood, and after that we do sampling, and this sampling might be take quite some time in your local computer if it is not strong enough. But PyMC have recently have another sampling bucket called nutpie, which is a lot of bit faster than this one. I will show you later, a little bit later, to improve or reduce the speed, because here as you can see it's quite long to sample. But anyway, after that we can fit our data set for LCM, something like that. So that this work is supported by Google Summer, of course, and NumFocus and the PyMC team. So I will have another example here that I put it in my website. And so basically the data set here we have is the internet rates for US, UK, and Australia. So here is the data set. So data set here I get from different central bank in different country here, and here is the three time series data for that three country. And I do the same thing as using the ICM model or LCM model to model that three data set. And here is the prediction as well. And this one is that I use some free panel Horowitz bucket to visualize it and put it in GitHub page. So if you click on this one, it might run a little bit slow as the start, because it's loading some packets called PyODI here. but after that you can see it's something, and if you click on this one, and so this one is just, and I mentioned here, is just for technology demonstration purpose, not for investment decision making, but it's so that if you have some expert domain knowledge as well, right, you can maybe incorporate other things here as like select different kind of kernel, or maybe incorporate thing like inflation rate, maybe, because inflation might be affect the interest rate. And in this one, I have one trick here is for sampling is I use nutpie instead of using the default sampling here. So if we use default sampling here, the time will be might be around 15 minutes. But if we use nutpie, which is also one project in PyMC, PyMC team, we can reduce it to like around 4 minutes. So it like 4 times faster. So I think this kind of feature will be incorporated in PyMC soon. But if you want to have a try to see how it works, you can also do the same thing, like just include nutpie and then compile that model, and then sampling just compile model using nutpie. That's it. I will start from here, and happy to answer any question you have.
All right, Dan, we have a couple of questions on the discourse. So trying to figure out the best way to do this. Do you want to try going to the PyMC discourse real quick? I think that your topic will be on top. And you can keep showing your screen if you don't mind.
So Discord, I don't think I opened. Oh, you mean the Discord of PyMC, right?
Yes.
Yes.
There we go. I'm betting your talk will be right on top. Yes. Can you click on your go down one?
This one.
There we go. Yeah, there's a couple questions if you right there. Here's the first one.
Oh, the question about how important the joint normality assumption is. So I guess here is what's it called? If you want to know. So the reason, first of all, for Gaussian process that we select a normal distribution, because it have some characteristics that help to calculate the Portiro and do sampling faster. Because if we multiply a Gaussian distribution with a multiple distribution, it will be a Gaussian distribution, and if we sum it up, it will become a same as well. And for multi-output, yeah, I think that question is, I understand the question, but I still not have the answer yet. So maybe let me have a look at more detail and answer it in this channel. But I get there is some reason or some limitation of Gaussian processes is it's quite slow. It's quite slow, and there is a lot of research. They try to make it scalable because for bigger data set, and also there also a direction to convert it into different kind of like it not linear or something, but more non-linear. Anyways, this one I think I need some time to understand this and answer it later. Yeah. For those I think that's one.
There's a couple more.
In the Bayesian sample, what is the Bayesian come with this one as well? I'm actually not sure, from that, because the data set I get from Chris, and what they want is at that time they want to model the average spin rate of different player, but I'm not sure how they use it in the business case. Like for the interest rate prediction, the data I collect is, so the aim is to predict the future interest rate. So that it might be one business case, but for this one, I guess is might be for the next game of the two teams, they might can using that historical performance of the players or the average spin rate to measure the next game performance of different players, and maybe behind that they have some kind of sum up the performance of the whole team, but I'm not sure. Yeah, so to be honest, I'm not sure for the baseball example how it will benefit a business standpoint. But if you see here, is it's not only can help to infer the missing date here, right? But can also help to infer the future game here. In this one, I add like prediction for the next 2 weeks, so we can see also the livelihood or the performance of these players in the next game if they happen, if that did happen, and that might be useful for the people to betting or doing something. I'm not sure, but that might be related to some business point of view. Yeah. The right side of the plot, the ZP are not going to extrapolate well. That is a good point, because this one we use our kernel as a exponential quadratic, and that kernel equals stationary kernel because we have x minus x prime square, right? So it calls stationary because x minus x prime. So if we move x to different places, but the distance is the same, the value of kernel is still the same. And this kind of kernel have a tendency to go to the mean. So if you see that this one, it will go to the mean of that. So here the example is just show us how to implement it, but you will need some kind of expert knowledge to choose suitable kernel to model this one. So maybe if it not go to the mean, there is some characteristics that you need to incorporate in that, depend on how you select the kernel. And because this is just in an introduction, but in so in the kernel function we have here, we only introduce just a bit, right? But 1 second, let me, this one. We have a lot of other kernel as well, and some is called stationary kernel, but some is not stationary. And I think there is a paper on this detail about how you use which kernel for which feature, and so this needs some kind of expert domain knowledge to incorporate in that model to select the suiker node to get the better prediction or the better as the inference. Same thing for this one, right? For interest rate. Here I just demonstrate as using a simple kernel, But as I mentioned, this is just for technological demonstration. I'm not an economist, so if you need some input for domain knowledge as well to have a more useful model. Yeah. All right. I think that's hope to answer this one. Was thinking there was a way to add to get a fan or teardrop shape. I'm quite not sure if Ravin, do you know what is a fan or teardrop shape? I'm not quite understand this.
It's just the shape of the distribution. But in the interest of time, we can answer this one async. I have one question on the Zoom chat. It's a long one, so let me read it out to you. I'm a beginner PhD statistics student, and my research is focused on predicting spatio-temporal crime hotspot patterns at high resolution. However, one major challenge is data sparseness, as crime occurrence is relatively rare. I want to exploit cross-correlation of multiple crimes to improve predictive accuracy. Do you think it's feasible to use the kind of techniques discussed here to help model the spatio-temporal distributions of crime types? I may need to use a Poisson process for counts instead of Gaussian processes, but I still wonder if it would help in solving the data sparsity issue. I'm going to paste this in the chat as well, just so you can.
Yes. I can see the question as well. No,
okay, great.
Yeah. Yes, I think my suggestion is it worth a try. I think because the data set have some spatial temporal characteristics, and is it what the Gaussian process and multi-Gaussian process built for this kind of data set actually. And there is I think in PyMC Discourse, if you should, there is some people modeling the same kind of spatial temporal data set, but not for crime ratio, but for others like I think some material in the land of different location, or for mining stuff, if you mining gold, for example. So I think this also have some similar problem like this one. So I think it's equal to try to search in PyMC Discourse, because I think a couple of people they implement it for that just before as well. So when I search Gaussian processes in the PyMC Discourse, I have some people have some example on that. So definitely have a try and to see how it works. Yep. Hopefully it answers the question. Yep.
I think so. I think that that just about covers all of the questions we have. So with that, I wanted to thank everybody again for coming to this session. And I also want to thank our sponsor, Misplay. They're the first corporate sponsor of the web series. They generously are helping fund this conference as well as general PyMC development. So thank you, Misplay, for that. You can get more information about any of this, PyMCon, Misplay, or how to get involved, or even PyMC development on our website. So I hope to see you at another session, and thank you again all for attending today.
Yes, thank you, everyone.